Most machine learning models do not work directly on the inputs. Why? Because the input dimensionality is really high. As a result, the models are projecting the inputs into a latent space or an embedding space. So these representations or the points in the embedding space can be thought of as knowledge vectors or condensed versions of the input. Most generative models learn continuous latent representations, but the world itself is often discrete. For example, language. So a natural question appears. What if neural networks could learn discrete representations directly? That is the core idea behind vector quantized variational autoencoder or VQ-VAE. So traditional variational autoencoders work by encoding an input into a continuous latent vector which is sampled from a Gaussian distribution. This allows smooth optimization using reparameterization trick. So essentially there is an encoder and a decoder, and in between the representational space is a Gaussian distribution. So we are sampling a point from this continuous Gaussian distribution. But there is a major problem. When the decoder becomes very powerful, the model may ignore the latent variables completely. So our goal is to make these latent variables as knowledgeable as possible. But if the decoder is too much powerful, then the latent representations are going to be useless. This is known as the posterior collapse. VQ-VAE solves this by making the latent space discrete instead of continuous. So here's how it works. First, an encoder processes the input and produces a continuous vector. But instead of passing this vector directly to the decoder, the model performs a nearest neighbor lookup. And this is a lookup table. And you can think of it as a dictionary. The encoder output is replaced by the closest embedding vector, as you can see here. So instead of infinite latent values, the model selects one entry from a finite codebook. The latent representation becomes a symbolic index. So according to the paper, the posterior distribution becomes effectively one hot, and as a result, we can prevent the decoder from becoming too powerful. Now comes the challenge. Quantization is not differentiable. Gradients cannot pass through a nearest neighbor operation since this is a discrete operation. So the authors solve this using a straight through estimator. During backpropagation, gradients from the decoder are copied directly to the encoder output, and this is really effective. Training uses three losses, as you can see here: reconstruction loss, and we want to update the dictionary itself, and also for the stability of the network we control the embedding growth. Together these stabilize learning and ensure the model actually uses the discrete latents.